All right, folks, this is perhaps one of the most important sections that we will talk about for really the entire course, mainly because of how pervasive it is throughout all our other concepts and how useful these ideas become if we can use them in their entirety. So 2-6, and this is something that you spend a lot of time on in Algebra 2. I'm actually teaching this right now in my Integrated 3 class. Okay, so it is something that you've discussed. Okay, I even talked about this last year when I taught Algebra 1. Okay, and I know for certain I taught you this with geometry. Okay, it wasn't with functions in geometry, but it was with triangles and all types of different shapes that we did this with. But it's consistent. You did it in 7th and 8th grade as well with triangles and other shapes, and it's called transformations. Okay, and the word transform means changing or to change. Okay, if I'm going to transform something, I'm going to change it. Okay, so in this first video, I'll try to keep it short here, maybe 15-20 minutes. We're going to talk through a couple of these. Okay, and maybe even just talk in depth about how the notation is going to be kind of worked out when we see this stuff. Okay, but this is, part of mathematics. A lot of people think mathematics is about calculations, and that's actually a very small portion of mathematics. Mathematics is a set of rules designed to actually avoid calculations. Okay, so if you think about, like, the most basic thing that we've ever learned in mathematics was to count, and then we learned to add, and then we learned to subtract. Well, adding and subtracting are just avoidance techniques for counting. Okay, if I have $12 and I give $4 away and I want to know how many do I have left, instead of counting 1, 2, 3, 4, 5, 6, 7, $8 left, I learned 12 minus 4 is 8, and that's a quick way of counting. Okay, so subtraction, quick way of counting. And then okay, well, what's division? And well, division is a quick way of doing repeated subtraction. Multiplication is a quick way of doing repetitive addition. Okay, so what we find out there is that those are rules, those are concepts or procedures that allow us to circumvent calculation. Okay, or at least in that case, counting. So a lot of the stuff that we see in this procedure is going to be able to allow us to circumvent graphing and creating tables and that kind of stuff to end up with an image of our function. All right, so we're talking about vertical, what we call a translation. Okay, called a vertical shifting. But translate means to move. Okay, so vertical shifting says adding a constant to a function shifts its graph vertically, and that vertical shift is going to be upward if the constant is positive and downward if it's negative. Okay, so this is something we've talked about in the past. And now here's the thing, is that when we talk about this in this section, I don't care what f of x is. F of x can be anything it wants to be. Okay, it can be x, it could be 2x, it could be 3x, it could be half x, it could be 1/3 x, it could be any one of our parent functions that we ever can imagine. It could be x squared, x cubed, x to the 4th, x to the 5th. It could be square root of x, it could be cube root of x, it could be 4th root of x, it could be log base a of x, it could be a to the x, it could be sine of x. Okay, so this, all of the functions, all the infinite number of functions that we could ever imagine, okay, are represented by f of x. Okay, so we're going to be very generic about this, and the reason we're going to be generic about it is because all of our transformations exist in the same fashion regardless of the type of function. Okay, so instead of just defining, okay, well, this is x squared, and what does x squared plus c look like, and then say, okay, well, what does x cubed plus c look like, and then say, okay, well, what's radical x plus c look like, and then what's sine of x plus c look like. If we recognize that it doesn't matter what that is, we can condense at least those four down to just one notation, f of x plus c. Okay, so if c is greater than 0, then f of x plus c is going to be a vertical shift or a vertical translation. If f of x minus c, and c is greater than 0, so subtracting a positive number, that's going to be a shift downward. Okay, I think it's important to write this, because if I just say f of x plus c, but what if c was negative? Okay, well, it'd be plus minus c, which is just minus c. So I think that's critical to actually have that little caveat there. So I know that this c then is a plus like 3 or plus 5, and this is a minus 3 or minus 5. If I don't have that, I think it's important to talk about. I could say, well, c is, in this case, negative 2. Well, then f of x minus negative 2, well, that would actually be f of x plus 2. I think it's a shift down, but it actually turns into a shift up. So that's why that's important to have c greater than 0 there. It says the y-coordinate of each point on the graph y equals f of x plus c is c units above the y-coordinate of the corresponding point on the graph of y equals f of x. Okay, that's all this is saying here. I'm going to go over to GeoGebra here to confirm this relationship between these red and blue graphs. All right, so here all I've done is set up an applet with a parent function f of x, and then the way I've structured this is I just took, if I double click on this, you see all I've done is I said, okay, take f of x, whatever I've typed in up here, and now add c to it. And what it does then is it creates this slider c that I can actually change, and you see then that it changes c to 2.1 in this case, so I have x plus 2.1. But if you look at this, what's happening is that wherever I stop this slider at, we end up getting, if I look at this distance here from A to B, we get a distance of 4, which is consistent with the amount that we moved this function upward. Okay, so what is nice about that is if I know points that are on this parent function right here, okay, if I know 0, 0, 2, 2, 4, 4 exist on that, then I should know instantly that the same exact points exist on, get back to 4, the same exact points exist on this one, except for the y values are increased by 4. So here it was 0, 0, this is 0, comma 0 plus 4. This one was 2, 2, that point right there is 2, comma 2 plus 4. And you see it, obviously 2 plus 4 is 6. This point right here was 6, 6. This one here then is 6, comma 6 plus 4. And you see that it is indeed at 6, comma 10 then. So that's a benefit of knowing how we transform with a vertical shift a line. Okay, now we can go down as well, and so then we see that that distance would be 6.4. So now this point 0, 0 would correspond down here to the point 0, comma 0 minus 6.4. This point here is 2, 2. This one's going to be down here 2, comma 2 minus 6.4. So basically what we're seeing is that this here is subtracting my c from every y value that was a part of that function. Now, like I said, it doesn't matter what my function is. So if I go x squared, I should have the same idea. Okay. Now, when I have a point like 0, 0 on x squared, then the point 0, 5 shows up on x squared plus 5. just add 5 to the y value of this green function. So we have the point 1, 1 here, okay? So 0.11 on the green function, so then the 0.16 should show up on that function. Because all I'm doing is adding 5 to the y value of anything that was on this green curve. Okay, so you see then it's the same. I don't really care what the function was, the parent function was. If I understand it's a vertical shift, it's the same way I treated a vertical shift for a line. Okay, we can do it with, like I said, it doesn't matter the function. Let's go x cubed. If I go x cubed, and I can now shift up and shift down. Now, maybe some functions that you guys aren't familiar with. Let's go sine of x. Sine of x is this to 0. It's touchy. There we go. That's the sine of x. Okay, it's a wave function. So this point right here, okay, is actually the point pi comma 0. Okay, 3.14 comma 0. If I add, let's say, 4 to it, I would just have pi comma 4. So I added 4 to the y value. Okay, and I'm adding that same 4. You can see that this distance here between A and B never changes. It's always 4. Okay, it's always that C term. If we go like A raised to the x, let me fix that. Instead of A, let's use 2. So just an exponential function. We can see that all we do, if I have 2 to the x plus 3.2, that means I took the original 2 to the x, and all I did, I shifted up 3.2 units. So hopefully you've seen enough of those. Maybe one that's of importance to us here soon. The absolute value. Let's say absolute value of x. We get the same kind of concept. Okay, just moves it up and down. That's what this is getting at here. And that's what this is getting at. Okay, so it says, the graph of f of x equals x squared. Use that knowledge to help you graph these other functions. Okay, so here's the idea. So the way I like to do these types of problems, or just in general when I'm trying to graph something, in my mind, I know a series of points off of the parent function. We know on the parent function of x squared, we have -2, 4, -1, 1, 0, 0, 1, 1, 2, 4. Okay? Now I have that committed to memory. So if I'm really doing this by hand, if somebody asks me graph this, this just pops into my head right away. I don't write it down, I just know it. Okay? And then I say, okay, well, if I'm going to have x squared plus 3, then this number here is no longer 4. We're going to have f of x now plus 3. It's going to be actually 7. This is going to be 4. This is going to be 3. This is going to be 4. That's going to be 7. So then the ordered pairs that I plot are -2, 7, -1, 4, 0, 3, 1, 4, 2, 7. And it's a much quicker process. And I don't ever write it down, but that's the train of thought that I go through when somebody asks me to graph x squared plus 3. I always think, okay, well, what's x squared look like? What are the ordered pairs there? What's that plus 3 do to that ordered pair? Does it mess with the x? Does it mess with the y? And then I adjust that on the fly, and I get that graph or the information necessary to graph that graph. Okay, do the same thing with x squared minus 2 then. So it'd be -2, 2. It'd be -1, -1. It'd be 0, -2, 1, -1, and 2, 2. If I was going to graph that one. I want to stop there. I don't think in 5 minutes I'll get through talking about horizontal shifts. So we'll pick up next time with horizontal shifts, which is a very similar concept as vertical shifting. Okay, but vertical shifting was messing with the y value. Okay, we can see here that if I go from f of x to f of x plus 3, the x's stayed the same. It's the y values that changed or transformed. When we do horizontal shifting, because we're going to be shifting left and right, and that's on the x-axis, it's actually going to be the x values that are altered, but it's done in a little bit different way. So I want to spend a little bit more time next session talking about that in great detail.